Hi everyone. In this lecture, I'll discuss a very interesting topic on digital inverters, which are normally posed to students before they come for projects. Or it's something that's good to know as an analog design engineer. So shown here is a CMOS inverter circuit and with driving a load capacitor of value CL. It's given that I'm driving this CMOS inverter with a clock signal of two different rise times. In the first case, let the rise time be TR. In the second case, the frequency is the same, but I am driving the rise times are almost doubled. And when you measure the power that is drawn from the supply, it turns out that the power has doubled. Now remember, the supply voltage remains the same, the input high voltage levels, all of that remains the same. The only difference is a change in the rise time. And you observe that the power dissipation in this inverter has doubled. Why is that? I mean, can we explain why is that the case? Now, most of you have just studied some basics of CMOS inverters. You know that the power dissipation is simply given by the load capacitance times VDD square times the clock frequency. The clock frequency is fixed, supply voltage is fixed, load capacitance is fixed. One would expect the power dissipation also to remain the same. But I'm just telling you that I've doubled the rise time, but suddenly you see that the power has nearly doubled. So then, what could be the reason for that? In the second example, I'm decreasing my clock frequency by a factor of half. I'm decreasing my clock frequency by a factor of half, but you observe that the power dissipation remains more or less the same. It doesn't change at all. Okay, so again, we should be able to explain why does this happen. Even though I'm decreasing the clock frequency by half, you don't see any change in the power dissipation. Now, the answer, I mean, if you directly look at the expression for power dissipation of a CMOS inverter, you will readily say that the clock has reduced by half, so you would expect the power to go down by half, but that's not happening. And why is that? Similarly, the third case I can introduce is that I'm changing the load capacitance. I'm almost say doubling the load capacitance. Again, I see no change in the power. So what could be the reason for that? If you just directly use this expression for power dissipation of a CMOS inverter, you would say that doubling the load capacitor should double the power dissipation. Okay, so then, but it doesn't happen. So what could be the possible reasons for that? Now, to answer these questions, we have to understand the power dissipation mechanisms in a CMOS inverter. Now, in this lecture, probably in a lecture or two, I'll talk about the different sources of power dissipation in a CMOS inverter and how do they change as I change the frequency, load capacitance, or the rise and fall times. So when we talk about the power dissipation in the CMOS inverter, there are generally three kinds of power dissipations. One is what we call the dynamic power dissipation. I'll explain the definitions in a few moments. The second one is what we call the short circuit power dissipation. The third one is the leakage power dissipation. We will see how these three different sources of power dissipation change with load capacitance, frequency of the input clock, and even the supply and temperature variations. First, we will look at the dynamic power dissipation. Now, this is a very fundamental power dissipation. So this is the power, for example, an inverter, when I'm feeding a clock signal to a CMOS inverter. Now, let's assume for the time being the rise time or the fall time of the clock is 0. Whenever the clock signal goes from a logic high to logic 0, so that's the falling edge of the input clock, the output has to rise from 0 to VDD. So which means this capacitor has to be charged from 0 to VDD. Now, we have already seen this in the initial basic course on electrical sciences, that the total energy stored in the capacitor at the end after charging it to VDD is half CL into VDD square. We also discussed if this charge is being supplied by a constant DC voltage source through a lossy resistive path, then half the power will be lost in the resistor itself. It doesn't matter what the value of resistor is. Now in this example, even though it's a MOS resistor, your MOSFET will be in linear region, the PMOS, that's the charging path for the capacitor. It doesn't matter, even if the resistor of the MOSFET is non-linear, it doesn't matter. The power that will be lost will be equal to half CVDD squared in the resistor. So the total power that's supplied by the supply which is VDD, will be half CVDD squared, which is the energy supplied. This is the total energy supplied from the supply. The total energy supplied to the capacitor to charge it is half CL into VDD squared. Plus, you need to add another half CL into VDD squared, which is lost as heat in this MOS device. Okay, the MOS acts like a resistor, so it will be lost as heat. So the total energy supplied is CL into VDD squared. Now this is the energy supplied by the supply. Now we are interested in power. So the rate at which this energy is supplied is what we are interested in. Now if you look at the clock signal, when there is a falling edge transition, so that's you're going from logic high to logic low, then we have a current drawn from the supply. So the capacitor at the output is charged to VDD. It's charged to VDD. And you're going to draw charges only at the falling edge transitions, when you apply a falling edge at the input. Okay, or the output is rising from 0 to VDD. Only in those instances, you'll be drawing charge from the supply. At the rising edge, when the input goes from 0 to 1, your NMOS is turned on, and you will be discharging that capacitor which was previously charged to VDD. So you will actually be giving charge to the ground. Your ground will be sinking that current from the charge from the capacitor. So in every cycle, if I apply a clock signal which has both a rising and falling edge every cycle, you are going to draw this energy CL into VDD square once per cycle. Okay, so we can easily say the average power is the energy delivered per cycle. You're delivering this much of energy. The supply is delivering this much of energy in a duration of t seconds. So it will be EVDD by t, or 1 by t is f clock. So you'll get CL into VDD square into f clock. Now this power is what we call the dynamic power dissipation, which is if your input is constant, if you apply a constant input, this power will be zero. There will be no power dissipation because you don't have to charge. So this is a power that's associated with charging the capacitor from 0 to VDD. So it's called the dynamic power dissipation, and it is a function of the clock frequency. So the energy is CL into VDD square. Now the clock frequency tells you how frequently you're supplying this charge. If you have a high frequency clock, then you will be supplying this charge much more frequently, which means the power dissipation will be much higher. Okay, so if in a CMOS inverter, this power, the dynamic power dissipation, is independent of the rise and fall times of the clock. So here I've assumed the rise time to be 0 or fall time also to be 0. And this power only depends upon the frequency of the clock and not on the shape of the waveform. As long as the waveform goes through a logic high and logic 0, I don't really care about the shape of the waveform, as it only depends upon the frequency of the waveform. Okay, and this power also has a quadratic dependence on the voltage. So if you double the voltage, if you increase the voltage by say 10%, you should expect to see a 20% increase in the dynamic power dissipation. And it's again directly proportional to the load capacitor itself. So this is what we call dynamic power dissipation. And in the first question, we said that even though we were changing the clock frequency and the load capacitance, I just posed a question that the power, it looks like the power dissipation is not changing. So we clearly know that this dynamic power dissipation is not the dominant source of power dissipation of the CMOS input. So now we will look at the other source of power dissipation in a CMOS inverter, which is what we call the short circuit power dissipation. The short circuit power dissipation occurs because of finite rise and fall times of the input signals, of the input clock signal. Now, as the input signal is rising, so we analyzed previously that when the input goes from 0 to 1 or 1 to 0, suddenly, say for example, if the input is going from 1 to 0, instantly your NMOS will be cut off and PMOS will be turned on. And immediately the PMOS will then start charging the capacitor. But in reality, most clock signals will have a finite rise time. And if this rise time, because the rise time is finite, you will not have this sudden mode of operation where you have one device turning off and the other device turning on. Instead, you will have a gradual shift between one device to other device. There will be a gradual handoff between one device's conduction to the other device's conduction. So we will look at what happens when I'm applying a rising edge at the input. So the input is now going from 0 to VDD, and the rise time TR is the rise time. So that's given by VDD, the time it takes to reach VDD. So I'm just going to call that as the rise time. And the slope of this waveform is simply VDD by TR. Okay, here TR represents the rise time of this waveform. Now, initially the input is 0. So you would see the output is the capacitor is charged to VDD. So when the input signal goes from 0 to VDD,